Hello explorers and welcome to another video. Today it's Advent of Code Day 12. And today we are talking about planets, and we are out roaming around in the galaxy, and there are a lot of moons, and we want not to actually hit those moons, and the moons have a specific position in 3D space. So they have an X, Y, and Z coordinate, and we are going to figure out how the gravitational draw or gravitational pull of these planets actually will change their direction. I don't know how to pronounce that word, but their actual velocity and direction. And in order to do this, we have their space, and we look at how they are different from each other. So, for instance, if we have one x value of 5 and one of 3, then the one with 5 will go lesser, so it will go minus 1, so it will go more to x. And the one with 3 will go plus, so they will go towards each other. And if they are on the same x position, they will not change. And we will need to figure out how large the velocity will be for the planet, and then update their specific position after we have corrected the velocity. So if we look at this example they have here, they have 3 planets with some coordinates, and on the first step, no of them have any velocity. If we look at the second step, then if we take the position 2 here for the first planet, it's 1 from 3, so that's plus 1, and then 1 again, so that's minus 1. And then 2s, those are equal. So why is the value 3 over here? Let's see if we can figure this one out. No, it was minus 1. Now I get it. Okay, so it was minus 1. So in every case here, minus 1 is smaller than any of the other planets. So this means that it will have a value of 3. In this case, we have 0. And minus 10 and minus 8 are smaller, but 5 is larger, which means that it will have a y value of minus 1. So minus 1 plus minus 1 plus minus 1 plus 1 is minus 1. And then in the z direction, we start with a value of 2. And here we have minus 7, 8, and minus 1, and that's also minus 1. So this is the velocity it will create. And then on the next line here, here we will see that we go from minus 1 to 2, so that's these 3. We go from 0 to minus 1, it's minus 1, and then we go from 2 to 1. So this is the fully updated step in the first iteration here. So I will try to implement this little example here with these planets and figure out their velocity and do this specific printout, so we actually have all these values here and do these 10 steps. And then I will try what we are actually wanting to do is figure out with this puzzle input that we have over here, what will the position be, or what will be the total energy of the system after 1000 steps. And the total energy of the system is the velocity added up in any direction. So that means that we need to absolute those values. So either if there's minus 11, that means 11. And then the same goes for the position. So all of these together, and then times each other and then plus that up, and we get the total energy of the system. So I think we will need to figure this one out later on. First thing I will do is actually do this printout, and then I will do, yeah. So when I have a full solution for this one, it's a lot of math, then I will get back to you and we'll look at that solution. And I'm back. So there were a bit of math today, and a lot of different moons and stuff to update, and I got the result of 14,606. So let's see if that is the correct answer for the first puzzle today. It is! You get a gold star, I get a gold star, everybody gets a gold star! So let's see how we did that. First off, I created a moon. And I gave it an ID, and that's just to make it simple for myself, so the comparison will be as easy as possible. I thought first that I would go with the X, Y, Z coordinates, but they can actually be equal to each other. So I thought, why not just give it an idea, so it will be easy to remember which one is which. And then I set the X, Y, and Z coordinates in the moon, and I can also get the idea for comparison, as I talked about. Updating the velocity for this moon if against another moon. So if the other moon is larger than this moon, then we will push in that direction, so +1. If it's smaller, we will push in that direction, so -1. Else it will be 0. So that is what we will add to our velocity. And the same goes for Y and Z coordinates. So this is the update velocity function. And then we have the update moon position, and that's just adding the velocity to the actual moon coordinates. So we actually push the moon in that direction. Getting the actual energy of this moon is just the absolute coordinate of all the X, Y, and Z coordinates. That's the position energy, and the velocity energy is the same but with velocity. And then we will just multiply those together for some reason. I also have a function to print the actual moon, so I get that output that they had in the example, so I could actually look and see that I had the correct setup. And then the actual code here was setting up all the moons with the specific values. And then in this case we went through 1000 steps. And for each moon, we have this moon that we want to update, and then we have another moon. I call it IT as an iterator. And then I check if this moon that I want to update is the same moon as the one that I iterate, then I don't want to do anything. If it's not the same, then I will take my update moon and update the velocity against that moon. And I will do that for the whole go through all the moons and do all that update. And after that, because I can't actually update the position of the moon during calculation of the velocity, because then I will get the wrong velocity for other moons. So I need to wait until I have updated all velocities, and when I've done that, I go through and update all moon positions. And I had an output here as well, so I actually saw for each iteration what the actual moon position was, but I removed that to make it simple. And then I have this energy summation down here. So energy sum is like is equal to 0. I go through each moon, I print the moon, and then I get the energy for that moon and update the sum and print it out. So that was the solution for the first part of today. So I'll read up on the second part and I'll get back to you when I know what to do. Yeah, so the second part here was a little bit more interesting. You actually need to do all these calculations until all the moons are in the same position as where they started. So this will be an interesting one, that we actually need to figure out how many steps there are until they are in the same position as the start. And we have one example here where it should take 2,772 steps. So I will try to implement that one and see if I get that to work. And if it works, then I will try it with the larger sample. Hopefully that will, because they also say that if we do this with the other example that we had, it would take a lot of steps. So it might not be the most efficient way to simulate the universe. Maybe there can be a simpler way. But I will try to do this the mechanical way and see how far I get. Perhaps it takes too long. We'll see. I'll be back. And we're back, and it's actually the day after. Because the simple function that I put up here, just running a while loop through the moons that we had, it took about 10 minutes to run through the example, which was the hard example, and then I added the actual data that we have now and ran it through that and tried to figure out what it was. And you see here that I add a number and write out the result every million of iterations, and I compare all the moons, and then I print out the number when it's done, if it ever gets done. And I asked in chat, Kordsnack, where other people are trying to solve these as well, and they figured out that it would take me about roughly 560 days to do this with with a function that I hadn't actually optimized. And I asked a colleague today, and he's a little bit more sharp and had the problem a little bit more out of sync, so he could think in new ways. And I guess I was a little bit tired yesterday. And he figured out that, well, all these numbers are not connected to each other. They are actually separate numbers. You have x values and x velocity. You have y values and y velocities, and z values and z velocities. You don't have to compare them exactly together. You just need to compare them apart. So I thought that I'd try that out. So in this little function here, I have the same that we have in the other. I just created new functions to update velocity for z, y, and x, and update the moon position for x, y, and z. And I keep the old functions as well, and the same for compare. So I could just set a value after, or a specific character after each of these, and then I will run these through, and that will go quite fast. And the results that I get is 116,328, 161,428, and 231,614. And what I did then, I actually took one of these results and added it to a test variable here, and then I just did a modulus operation on each of these to see where they actually collide. And I got this huge number here, and as you see, my test is still running down here. So if we take one of those values, you see it's very far from the actual last value that I get here. I don't know if this is actually the correct value or if this is just some bogus value that I came up with, but let's try it and see if we get a gold star. You get a gold star, I get a gold star, everybody gets a gold star! So we actually solved this one too. Really nice. So this was today's example, the day 12 that we solved. I hope that you found this video interesting. I hope that you learned something. And I really, if you haven't subscribed yet and you like these kind of puzzles, or you like tutorials, or you like new interesting libraries that I find and I try to showcase here, then please subscribe. And I really hope to see you in the next video.